In this video, we're going to learn about sequences. So here we're given the sequence 3, 9, 15, 21, and we want to identify the following. First term, second term, third term, fourth term, last term, and A1, A2, A3, A4. Now, a sequence is just a list, and the terms are the items of that list. So the first term is just the first item of this list, 3, 9, 15, 21. And the first item is just 3. So that's the first term. You can probably see where this is going. The second term is just the second item of this list. 3 is the first item, so 9 is the second item. Therefore, the second term is 9. The third term then, 1, 2, 3, is 15. And the fourth term, 1, 2, 3, 4, is 21. The last term is the final item in the sequence. In other words, the rightmost item in the sequence, and that's 21. Now, in the right column here, we have a compact notation, A1, A2, A3, A4. Now, in general, AN is equal to the nth term. It's just a nice, compact, mathy way of writing it. So A1 is just the first term, and we know that the first term is 3. So A1 is equal to 3. A2 is the second term of the sequence. We know that the second term is 9. So A2 equals 9. A3, third term, we know that's 15. So A3 equals 15. And A4 is the fourth term, which we know is 21. So A4 equals 21. Here's our next problem. We're given that A1 equals 6 and AN plus 1 equals AN plus 2 for n is greater than or equal to 1. And we want to compute the first 5 terms of the sequence. Okay, so really we want to compute A1 equals something, A2 equals something, A3 equals something, A4 equals something, and A5 equals something. So what do all these equal? Well, we're told that A1 is equal to 6, but we're not told what A2 is. However, we do have this rule, AN plus 1 equals AN plus 2, that applies for n is greater than or equal to 1. So why don't we take that rule, write it down again, AN plus 1 equals AN plus 2, and let's just plug in n equals 1. Plugging n equals 1 into this formula, we get A1 plus 1 is equal to A1 plus 2, which simplifies A2 is equal to A1 plus 2. Okay, so now we've got an expression for A2. It's still in terms of A1, but let's go ahead and write it in there. A2 equals A1 plus 2. And we know that A1 equals 6. That was the first term. So this is really equal to 6 plus 2, which makes 8. Now to get A3, we can do a similar thing. We've already plugged n equals 1 into this formula here, so let's just go ahead and plug in n equals 2. So plugging in n equals 2, we get A2 plus 1 equals A2 plus 2, which simplifies. A3 is equal to A2 plus 2. And we'll go ahead and write that in here. A3 is equal to A2 plus 2. And A2 is equal to 8, so we can just go ahead and sub that in. So A3 is equal to 8 plus 2, which makes 10. We can keep on continuing this trend. So next thing we plug in, n equals 3, we get A to the 3 plus 1, so A4 is equal to AN, so A3 plus 2. And we plug that in for A4 right here. A4 is A3 plus 2. And A3, we already know that's equal to 10. So A4 is equal to 10 plus 2, which is equal to 12. And then do this whole process once more to find A5. The next thing we plug in is n equals 4, and we get AN plus 1, 4 plus 1 is 5, is equal to AN, so A4 plus 2. and we put that in for a5 over here. a5 is equal to a4 plus 2. a4 we found that's equal to 12. So we have 12 plus 2, which is equal to 14. So there we go. There are the terms of the sequence: 6, 8, 10, 12, 14. Let's write that down here. 6, 8, 10, 12, 14. And looking back, in hindsight, this becomes very obvious what's going on. Starting at 6, we're just counting up by 2. 6, 8, 10, 12, 14. And we see that happened because this rule here, called the recursive rule, said that to get the next term, we always take the previous term and add 2. a2 was 6 plus 2 to make 8. a3 was 8 plus 2 to make 10. a4 was 10 plus 2 to make 12. a5 was 12 plus 2 to make 14. Even when it's just n in the recursive rule, this is clear because an plus 1 is the term that comes right after an. So this rule is saying that the next term of the sequence is equal to the previous term plus 2. And that's exactly what we see here. Here's our next problem. What is the fifth term in the sequence defined by f of 1 equals 0, f of 2 equals 5, f of n equals 2 times f of n minus 1 minus f of n minus 2 for n is greater than or equal to 3? Okay, well, first of all, f of n, that's just another notation for an. And it works this way because the sequence can be interpreted as a function whose domain consists of the natural numbers. So the fifth term here is going to be f of 5. So that's what we want to find. We want to find what is f of 5 equal to. And since this is a recursive rule, we know that f of 5 will be defined in terms of previous terms, which themselves will be defined in terms of even more previous terms, and so on. So why don't we start with the terms that we know. We know that f of 1 is equal to 0, and f of 2 is equal to 5. And then we'll find what f of 3 is equal to, and then we'll find what f of 4 is equal to, and then we'll find what f of 5 is equal to. Alright, first f of 3. Now we're not given f of 3, we're only given f of 1 and f of 2, so this is a good indication that we're going to have to use our recursive rule here. This recursive rule applies for n is greater than or equal to 3, so why don't we just go ahead and plug in the lowest value possible, n equals 3, into this rule, and we write down what we get. So plugging in n equals 3, we get f of n, so f of 3, is equal to 2 times f of n minus 1, so 2 times f of 3 minus 1, and then minus f of n minus 2, so f of 3 minus 2. And let's simplify this a bit. So this is equal to 2 times f of 3 minus 1 is just 2, and then minus f of 3 minus 2 is just 1. And hey, we know what f of 2 and f of 1 are, so we can use that to compute f of 3. So f of 3 is equal to 2 times f of 2. F of 2 is just 5. Then minus f of 1, and f of 1 is just 0, so minus 0. So 2 times 5 minus 0, that's 10 minus 0, which is equal to just 10. Now we can do a similar thing with f of 4. So we just plug in the next value of n into this formula, plug in n equals 4. So we get f of 4 is equal to 2 times f of 4 minus 1, so 2 times f of 3, then minus f of 4 minus 2, so minus f of 2. And hey, we know f of 3, that's just 10, and we know f of 2, that's just 5. So let's go ahead and plug it in. So this is 2 times f of 3 is just 10, and then minus f of 2. F of 2 is just 5. So 2 times 10 is 20, and then minus 5 makes 15. We just go through this process one more time to find f of 5. So plug in n equals 5 into this formula, get f of 5 is equal to 2 times f of 5 minus 1, so times f of 4, and then minus f of 5 minus 2, so minus f of 3. And that's equal to, we just grab that f of 4 is 15, and f of 3 is 10, plug them in, So 2 times f of 4, which is 15, 2 times 15, and then minus f of 3, which is 10. 2 times 15 is 30, and then 30 minus 10 is 20. So there we go. There's the fifth term in the sequence. F of 5 is 20. Before we move on, let's just look back and translate this recursive rule into plain old English. Notice that the term before f of n is f of n minus 1, and the term before f of n minus 1 is f of n minus 2. So this rule just says that to get the next term, we take 2 times the previous term minus the term before that. So we're given 0 and 5, and then to get the next term, we take 2 times the previous term, so 2 times 5, minus the term before that. So 2 times 5 is 10, then minus 0 is 10. Apply that again to get to the next term. So take 2 times the previous term, 2 times 10 is 20, then minus 5 is 15. Apply the rule once more to get f of 5, that's 2 times the previous term, 2 times 15 is 30, and then minus 10 makes 20. So yeah, makes sense. Here's another problem. This time we want to work backwards. We want to find a recursive formula for the following sequence: 0, 1, 1, 2, 3, 5, 8. First, let's see if we can spot the trend in the sequence. Are we adding or subtracting by the same amount? Well, first we have a plus 1, then a plus 0, then a plus 1, then a plus 1, then a plus 2, then a plus 3. No, we're not adding by the same amount. Are we multiplying or dividing by the same amount? Well, 0 times... You can't multiply 0 by anything to get 1. So that's a bust also. Even further on in the sequence, 1 times 1 makes 1, but 1 times 2 makes 2, and then 2 times a fraction, 2/3 makes 3, so no, not multiplying by the same amount either. But hey, look at this. When we add 0 plus 1, we get the next term, which is 1. And then when we add 1 plus 1, we get the next term, which is 2. So it looks like to get the next term, we just add the previous term and the term before that one. So 1 plus 2 makes 3, 2 plus 3 makes 5, 3 plus 5 makes 8. Yeah, that all checks out very nicely. So how do we write down this formula? Maybe it's easy to start by stating it in plain old English. We'll write down that the next term is equal to the previous term plus the term before the previous term. There we go. So we've got a word formula here, and now we just need to translate this into math. How about we call the next term an? So an equals the previous term. What's that? Well, the term before an is just an minus 1. And then plus the term before the previous term. The term before an minus 1 is just an minus 2. Now we're almost done, but we're not done quite yet, because this rule only starts applying at the third term of the sequence. We can't really apply this rule beforehand, because in order to apply the rule, we need 2 terms before the next term. So this rule only holds for n is greater than or equal to 3. Okay, so now we've got a rule that defines the third, fourth, and so on terms of the sequence in terms of previous terms, but we still need to consider the first and second terms. We need to state those explicitly. So the first term, a1, is equal to 0. And then the second term, a2, is equal to 1. And then we've got our recursive rule. So here we go. Here is our recursive formula for the sequence. Now note that although this is a perfectly valid answer, there are also other perfectly valid answers as well. We could have just as easily said a1 equals 0, a2 equals 1, and then changed up this recursive rule a little bit. Maybe say an plus 1 is equal to the previous term, which would then be an, plus the term before that, which would be an minus 1. Again, this rule only starts working at the third term of the sequence, so the very first value we could plug in for n would have to make n plus 1 equal to 3. So we'd need n is greater than or equal to 2. So this would be a perfectly fine answer as well. Or maybe we wanted to take things a step further and define another perfectly fine answer. a1 equals 0, a2 equals 1, and then how about say n plus 2 this time? An plus 2 is equal to what's the previous term? Well, the term before an plus 2 is an plus 1, and then the term before that is just an. And again, the recursive rule would only start applying for a3, which would mean the very first value for n would be 1. So n is greater than or equal to 1. So that would be also another perfectly valid result. All of these rules are equivalent. They all represent the same idea that we start off with 0, then our next term is 1, and then after that we get the next term by taking the previous term plus the term before the previous term. And in fact, there's even a name for this sequence here. This sequence is known as the Fibonacci sequence. So now that we've been introduced to sequences, we'll continue to learn about special kinds of sequences, such as arithmetic sequences.